Hello and welcome to the class. So in this lecture we are going to discuss about the proportional, integral and derivative control. So these are the few different type of control actions. They are the automatic controls actions. Okay. So in this we are going to learn about how we are going to control the system, we are going to decrease the error. One you can say that by proportionally and integrally and derivative actions. Okay. So first of all, let's have a brief overview of this. So you all know that in an automatic control system, simply it is used to maintain its output within desirable limits. कोई भी अगर output आपका limit से ज़्यादा जा रहा है, so just we try to decrease that you can say the limit or the difference between the desirable line and the error and the output which is coming. So we are going to decrease that error basically. Okay, so any deviation of the output from the reference input is detected by an error. We all know that in a feedback system there is a feedback system. If we are going to give any output, then we have the here we can detect by having the feedback system. So the error, whatever the error may be there, we can control it proportionally, integrally and derivatively, so that we should get the desirable output, or the we can reduce that error. Okay, so any deviation by this feedback system, we can see that that the output is deviated or not. If it is deviated, then we detect that error. Then the error thus detected is used as an actuating signal. We use that error as an actuating signal for control action. Okay, through the controller. There are the controllers which are being used so that we develop the actuating signal simply proportional to that error and give to the system. Okay, so the proportional control action and the types of control actions used for improving transient, both the output and the transient and steady state response. Steady state response of a control system we have. So how we are going to reduce that error, we are just simply going to learn that. Okay, so first of all, let's discuss about the proportional control. So here is a simple block diagram shown over here. So you can see that we already know some of the terms which are mentioned over here. This is a simply reference signal. You can say that this is the input or the reference signal, and this is the output which we can say write as CS. Okay. Then you see that this is the feedback going on over here, and the feedback is given over here, which is the BS. We have considered the feedback signal as the BS. So RS minus BS, ES is simply the error signal. Whatever the error and the deflection, or you can say that your output deviation is there, it will give over here, and the error according to that, the proportional error you will get at this point. Okay, then this error signal will develop the actuating signal proportional to that particular error, and again we are going to give that actuating signal to the system, and according to that we will get the output over here. Okay, so this is a simple system working, and the proportional control work like this. Okay, so in a proportional control, the actuating signal, this actuating signal for the control action in a control system is proportional to the error signal. Okay, so this actuating signal is proportional to the error signal. Okay, the error signal being the difference between the reference input, what just I told you, error signal is just the difference between the reference signal and the feedback signal, okay, which is obtained from the output. Okay, so for the system we have considered the actuating signal proportional to the error signal. Therefore this system is simply called as proportional, as written over, proportional control system. Okay, proportional control system. In this system we just want that the control system should be underdamped. Okay, the system should be underdamped. Okay, why underdamped? Because if the system is underdamped, then we will get the quick response, and an underdamped control system exhibits exponentially decaying oscillations. in the output time response during the transient periods. Okay, during the transient period we have the exponentially decaying oscillations. Oscillations उसके जो होंगे वो आप जानते हैं, उसके अंडर डैम कंडीशन के अंदर we have in the last lecture we have go through the under dam conditions, over dam and critically dam condition. You must remember the oscillations which are being developed in the under dam condition. So it's oscillations just going to decay with the time response. All right. So this is simply about the proportional control system. So now let's move forward for the derivative control. Okay. So let's discuss about the derivative control now. So for a derivative control action, the actuating signal consists of the proportional error signal added with the derivative. Okay, actuating signal consists of what? It have both the signals, that is a proportional error signal, okay, and what second thing should be there? Second thing should be derivative of the error signal, okay. So we have both of these signals in the actuating signal. Therefore the actuating signal for the derivative control action, actuating signal simply given by EAT, okay, and we write this as AT, okay, AT, and plus derivative signal det over dt, okay. So where TD is simply your constant, okay. So we have both the signal, that the proportional signal plus the derivative of the error signal. All right. So if we are going to take the Laplace transform of the actuating signal, just take the Laplace transform of this, then what we will get? We will get EAS is equals to ES plus, since this is the derivative, so the Laplace of the derivative signal is simply S TD. This should be capital, sorry, it should be ES, okay. So this is simply the Laplace transform of the actuating signal. All right. So for the second order unity feedback control system, we have the block diagram representation, okay, using the derivative control action. We have included the derivative control action over here. You can see that the feedback is coming from here, which is should be the give the error over here. So this is the input signal, this is the feedback signal coming over here, and RS minus this signal should be the error signal being generated over here, okay. So this error signal is moving over here, and with the derivative of the error signal, this should be the proportional error signal, and this should be your derivative of the error signal, and both of these signals are getting summed up over here, add up over here, and according to both of them means the proportional error signal and the derivative of the error signal, we are getting the actuating signal. That actuating signal we are giving to the system, and according to that we get the output, okay. So both the proportional and the derivative control action are taking place in this block diagram. So we have just simplified this and solve further, so we get this block diagram, okay. So by using this block diagram, let us write down the overall transfer function of this closed loop second order system using derivative control, okay. So overall transfer function of this should be CS is your output divided by RS, okay, which should be what? 1 plus STD, okay, into omega n square, giving over here in this block diagram S upon S 2 zeta omega n divided by 1 plus STD into omega n square upon S plus 2 zeta omega n, okay. So this is what we are getting over here. Let's simplify this. We will get 1 plus STD into omega n square, all right, divided by s square plus 2 zeta omega n plus omega n square TD plus s should be there plus omega n square. All right. So from here, from this equation, you can see that the characteristic equation of the above the characteristic equation of overall transfer function is, what is that characteristic equation? Characteristic equation should be this, okay, which is s square plus 2 zeta omega n plus omega n square TD to s plus omega n square equals to 0. Okay, so this is the characteristic equation. So if we are going to compare this characteristic equation, then you can see here that what should be the damping ratio. So the characteristic equation using the derivative control action, you can see that the damping ratio should be given by, we just consider zeta dash, and zeta dash should become 2 zeta omega n plus omega n square TD upon 2 omega n. Okay, we should become zeta dash is equals to zeta plus omega n TD by 2. Okay, so this should be the damping ratio of this characteristic equation. How? If you are going, might be you remember the, you can see that damping ratio is simply what? Zeta. In which equation? In the standard, simply you can say that the characteristic equation of when the second order transfer function, when we are just not going to take the derivative action. So what was the characteristic equation in that condition? Characteristic equation was s square plus 2 zeta omega n plus 2 zeta omega n s plus omega n square equals to 0. So this was the characteristic equation when we didn't consider the derivative control. So from here you can see that what should be zeta. So zeta should be this much. Okay, you can consider s is here, 2 zeta omega n, just put it equals to this. Okay, from here you calculate the zeta, so you will get 2 zeta omega n plus omega n TD, omega n square TD. Okay, this divided by 2 omega n, so this zeta dash will become equal to this. Okay, so we have just compared that characteristic equation, okay, without derivative control and with derivative control, and then we have put the damping ratio in this condition. So the damping ratio of the characteristic equation when we are going to consider the derivative action should be this. All right. So from the this block diagram, we can also write a forward path transfer function, and the feedback path transfer function. What is the feedback path transfer function? Okay, so the forward path transfer function should be in a block diagram, the forward path transfer function is simply you consider as GS, which should become 1 plus STD, okay, omega n square upon S bracket S plus 2 zeta omega n. Okay, and the feedback path transfer function is HS is equals to 1. Okay, so the transfer function relating ES and RS, ES just go to the block diagram, you will know that. So we have already studied earlier. So the transfer function, relating ES and RS is, so ES upon RS should be what? 1 upon 1 plus GS, sorry, it should be HS. Okay, and what are the value of the GS and HS? Just we have got the value of the GS from here and HS from here, and put both of these values GS and HS in this equation. Okay, we will get the transfer function relating to ES and RS. So what should be this? 1 upon 1 plus STD, okay, omega n upon S into S plus 2 zeta omega n, okay, into 1. Okay, HS is simply 1. So just simplifying this equation, we will get what? We will get S plus 2 zeta omega n divided by S square plus 2 zeta omega n plus omega n square TD into S plus omega n square. Okay, we will get this. This is simply the transfer function, which is ES upon RS. All right. Okay. Now you know that what is the ramp function. So here, for a unit ramp input, so if this is the ramp input, then RS should be is equals to 1 upon S square. All right. So ES is equals to what? ES is equals to 1 upon S square, S into S plus 2 zeta omega n divided by S square plus 2 zeta omega n plus omega n square TD into S plus omega n square. Okay, so we have just put the value of RS is equals to 1 upon S square over here. Okay, so we are getting ES in this form. All right, so the steady state error, we all know that the steady state error for a unit ramp input is determined as the steady state error. For unit ramp input is, you know that ESS should be equals to limit S tends to 0 S into ES. Okay, which will become what? Just limit S tends to 0 S into ES. We have ES in the above equation, just put it over here. S into 1 upon S square to S plus 2 zeta omega n divided by S square plus 2 zeta omega n plus omega n square TD S plus omega n square. Okay, when we are going to put this value, we will get what? We will get 2 zeta upon omega n. So this is the steady state error. So from this expression, we conclude that the steady state error is not affected by the derivative control action. Okay, so as the derivative of the error is used in actuating signal, and as such, if the error varies with time, okay, if the error varies with time, then in that case the derivative control reduces the error. All right, so but one thing is there, if we are going to compare the transfer function of the second order control system where we haven't considered the derivative control, and in the system where we have considered the derivative control, we are getting one extra term over there. The natural frequency omega n is unchanged, but we are getting 1 0 over there, which is S is equals to minus 1 upon TD. Okay, in that equation we are getting. So here we are going to discuss about the integral control action. In the last topic we have discussed about the derivative control. So in an integral control action, the actuating signal, it simply consists of both the it is simply the sum of, you can say that, the addition of both the proportional error signal, okay, and integral of the error signal, okay, integral of the error signal. And this is very easily you can see in this block diagram shown over here. We have simply the input over here, the output CS is over there, and you can say that we have the feedback. Okay, so and the feedback is coming from here, it is giving the error, simply error, ES should be the error we are getting over here. So in this line it is moving the proportional error signal, here it is moving the integral of the error signal, and both of these error signals are getting summed up or added, and they are getting added over here. Okay, and then after that we are getting the actuating signal in light of both the proportional error signal and the integral of the error signal, and that actuating signal is going to the system, and according to that we are getting the output. Okay, so this is how we are going to reduce the error in the output by using the feedback control system, and by using the proportional error signal and the integral of the error signal. All right, and this in the second block diagram, this is simply the simplification of the above the first block diagram. All right, so as we say already that this is simply the sum of the proportional error signal and the integral of the error signal. So the actuating signal is simply given by actuating signal, EAT is given by what, the proportional error signal plus KT integral of ET dt. Okay, the integral of the error signal. All right, where Ki, where this is not KT but this should be Ki, because it is the coefficient of the integral error signal. Okay, so where Ki is simply constant, Ki is constant. Okay, just let's take the Laplace transform of the above equation. Then if we are going to take the Laplace transform, what we will get, EAS plus this should be ET plus Ki ES over S divided by S. All right. So for the second order unity feedback control system, the block diagram as shown over here. So the transfer function of this closed loop block diagram should be what, the transfer function of the second order closed loop transfer function with the integral control is given by transfer function of closed loop is simply what, CS upon RS. That's this should be what, 1 plus, here you can see that, or here in this block diagram you see 1 plus Ki over S, 1 plus Ki over S, you can see it is giving already in this block diagram, into omega n square divided by what, S into S plus 2 zeta omega n. Okay, this divided by 1 plus Ki over S into omega n square S into S plus 2 zeta omega n square. Sorry, not the square is there, only zeta omega n. Okay, means GSHS upon 1 plus GSHS. We have already discussed what is the transfer function. Okay, after simplification what we will get? After simplification we will get simply S plus Ki into omega n square divided by S square plus 2 zeta omega n s square plus omega n square s plus ki omega n square. Okay, this is simply the overall transfer function of that closed loop. So in this, the characteristic equation of this should be what? The characteristic equation of the overall transfer function will be s square plus 2 zeta omega n s square plus omega n square s plus ki omega n square. Okay, this is equals to 0. So this is the characteristic equation of this system. Sorry, this is a mistake. It should be s cube. S cube will be there. S cube. So you can see that here the characteristic equation is of third order, since s cube is here. So by using it was shown by using the Rutherford's criteria that if we have 2 zeta omega n less than ki, then what? Then out of three roots of the above characteristic equation, 2 roots have positive real part. Okay, have two roots have positive real parts. Then what? If it is have positive real parts, then we have already discussed this, that if any root have the positive real part, then that system is unstable. Okay. Second condition is this that if we have 2 zeta omega n greater than ki, then all three roots have negative real part. Hence system is stable. All right. So let's move forward. If you are going to consider the block diagram shown above, if we going to consider that, then we have two paths over here, that is the forward path and the feedback path over here. So just we are going to write down first of all separately that what should be the transfer function of the forward path and what should be the transfer function of the feedback path. So the transfer function of feed forward path, you can say that, or you can say that forward path. Okay, this should be simply gs is equals to s plus ki omega n square divided by s square into s plus 2 zeta omega n. All right, and feedback transfer function is hs is equals to 1. Okay, if we are going to relate as we have related in the derivative control action, that if we are going to relate or we are going to calculate the transfer function relating es and rs, then the transfer function should be given by es upon rs. This should be equals to 1 upon 1 plus gs into hs. Okay, and the value of gs and hs is given over here. Gs is here, hs is here. Just put it over here, 1 upon 1 plus, okay, what will be gs? S plus ki omega n square divided by s square s plus 2 zeta omega n. Okay, into 1. This is a transfer function. Just simplifying this, we will get what? We will get s square into s plus 2 zeta omega n divided by s cube plus 2 zeta omega n s square plus omega n square s plus k I omega n square. Okay, from here you can see that if we are going to write Es over here, and we can write down Rs over here. If we are going to give any input over here, then we can easily get the output. Okay. So for the second order control system, in case of integral control action, the error, okay, the error is given by this equation, all right, and it can be shown that if the input is unit ramp function, that is, if we are going to give Rs is equals to 1 upon s square, Rs is equals to 1 upon s square. So if we are going to give the unit ramp input, ramp input should be there, then in that case the steady state error ESS, this should come out to be 0, rather than in that the earlier condition, if we are going to consider that without using integral control, the steady state error in the case of second order control system, the unit ramp input, for a unit ramp input, then the steady state error in that condition comes out to be 2 zeta upon omega n. This is with integral control, and this is without integral control, all right. So here let's consider this one more condition, that the steady state error for a parabolic input in the case of second order control system is infinite. We have studied that earlier, in the steady state error in case of parabolic input. But if we are going to consider the integral control action, then for the parabolic input, that is Rs is equals to 1 upon s cube, the steady state error using integral control should be given by Es is equals to, simply we have this equation as shown over here. We are just going to put instead of Rs 1 upon s cube over here. So 1 upon s cube for a parabolic input, we have s square s plus 2 zeta omega n divided by s cube plus 2 zeta omega n s square plus omega n square s plus ki into omega n square. Okay. After simplification, just ESS is equals to limit s tends to infinity, s tends to 0, sorry, s into Es. Okay, this will give us what?